Hello everyone, my name is Debashish Rai Chaudhary and I'm going to be presenting uh, legally binding anonymous multi-party commitments on a blockchain. My presentation would contain the following three sections. First, I will go through the context of what we are trying to achieve. Then I will discuss the designated deanonymizer ring signature, which is a ring signature that allows someone allows a designated party to de-anonymize the signer. And finally, I would be discussing the legally binding commitments that would be using this kind of signature. So to start with, we consider smart contracts. So smart contracts allow people to do a cryptographically ensured commitment on a blockchain platform. However, if you are doing this automatic sort of transactions, then you are sort of restricted to some form of cryptographic asset. So it can be generated directly by some cryptographic method. It can be like a proof of work reward, like that there are in Bitcoin or Ethereum and systems like that. Or it can be some tokenized form of a physical asset. For example, a dollar-backed coin or a gold-backed coin, in which case you need an arbiter to make sure that the physical assets are indeed correctly represented by the tokens, and it's like you are not creating out tokens out of thin air. However, contracts have much more to do than just automatic transactions. For example, I can make a commitment to build a house or build a software in exchange for some money. Now, if I am normally, people would go through like stick to their commitments without any issues. So if I promise to make a software, I hope to think that I will be making the software correctly, and I also hope that I would get paid correctly for the same. However, a contract always has the chance that someone would disagree, and in which case a court needs to get involved, or some form of an arbiter needs to get involved. So we are working with an optimistic situation when most of the time an external arbiter is not required, but we want to have the option of involving an arbiter when there is a dispute. And this arbiter can be a judge or any other system. And then we want to allow free decentralized signing of contracts on a blockchain platform with the assumption that most people will stick to the contract anyway, so the arbiter is not needed to intervene in every case. In detail, our objectives are as follows. Anyone with a verified public key needs to be able to post an advertisement for a contract. And by verified public key, I mean there has to be some trusted authority to rely on who would be responsible for associating the public key with the actual identity of the person or the party. This is similar in functionality to a certifying authority in the case of digital signature. It's exactly the same purpose, to associate the public key with the physical entity that is a party to the contracts. And then once that advertisement is there, other parties can respond to this advertiser anonymously, which means at this point the advertiser doesn't get to know who is responding to his request. But when they get into the contract, they have to know who is signing that contract. So the system is designed in a way that once they signed the contract, the system validates that all the contracts are only signed by validated users. So basically their signatures are using public keys that are registered to the system. And the parties get to know who are the other parties involved in the contract. It also, at the same time, gives some level of anonymity to each of the parties, in the sense that other unrelated blockchain users cannot know who are signing the contract. Now, in case there is a dispute, any party would want to be able to hold the others responsible, and they have to be able to show to any external party, like a judge or an arbiter, that the other parties indeed signed the contract. So they have to be able to not only de-anonymize them, they have to be able to demonstrate that their de-anonymization is correct to any court. And the trusted party is required to register the public keys of the parties involved. Now I want to talk about the designated de-anonymizer ring signature. To start with it, I will first like to discuss the point pair vectors. A point pair vector is a pair of points on an elliptic curve. So each point has two coordinates, but we are considering a pair of points. And you can easily check that this they do qualify for being vectors in the most obvious way. And we would consider them parallel or having the same direction if the discrete log of the second component with respect to the first component is the same for all of them. So there exists some W such that for every I, yi equals wxi. We can also call these parallel vectors linear. Now let's say we have an ordered set of tuples of point pair vectors. And if one of these tuples in the ordered set is linear, then we call it a linear member tuple of that set. Now, we're trying to construct a proof of, like, given a set of these tuples of point pair vectors containing one linear member tuple, we're trying to construct a zero knowledge proof of the fact that one of the member tuples is linear. So let's say we do have a tuple of point pair vectors x1, y1, x2, y2, and so on up to xn, yn. And what we do is we let a comma b equals x1 comma y1, and we construct c and d as a randomized linear combination of all the other vectors. So if we choose, say for example, 8j's, randomly from FQ, and we do this random linear combination of the other vectors, which answer to be C. And then if we can prove that A comma B is parallel with C comma D, then with a very high probability we can say that the vectors x2, y2 and x3, yc all are parallel to A comma B. And with this principle, we construct this proof. This is a very straightforward adaptation of the Monero ring signature. Here we choose a random R and random Cj comma Dj from FQ for every j other than k, k being the index of the linear tuple in this order set of tuples. And then as shown before, we compute A, B, and C and D, and we compute the commitments EJ and FJ. We compute a challenge H, and we compute the value of CK and DK accordingly, and the set of values CJ and DJ construct the proof. To verify the proof, the verifier simply computes the same values of H and computes AJ, BJ, CJ, and DJ for every J, and computes EJ and FJ with CJ, AJ, and DJ, BJ, and FJ equals CJ, CJ, and DJ, DJ, and computes the hash and checks the hash equals the sum of all the Ds. And this is basically this same thing we do in the Monero ring signature. So now that we have this proof, ZKP element MT, we can now use it to construct our designated deanonymizer ring signature. Here we consider M as a message, Q is the signer's private key, and deanonymizer's public key are PI indexed by I. So if you have multiple deanonymizers, each having a public key indexed by I. Now, since it's a ring signature, the signer chooses other public keys, Q1, Q2, and Qm, and arranges them so that Qk happens to be the public key of the signer. And then the signer computes Ri equals Q pi, and signer computes the linear tuple GQ and Pi Ri, so P1 R1, P2 R2, so on and so on. And then the signer computes the other tuples the same way. The signer uses the same value for P and R, and simply changes the value of Q, J, and then computes the proof, the ZKP LMT proof, as we discussed earlier. And this constructs the signature. Now, the verifier only has to check the ZKP LMT proof correctly. And the reason it works is because for some value of k, this has to be a linear tuple. So all of these values, Pj and Rj, Pi and Ri, have to be parallel to G, Gk, G, Qk. And that means for that pair, all of these R's are Q times P, small q times P. And so the deanonymizer can compute Q equals P inverse R for his own public key. This basically works as the designated deanonymizer ring signature. Now, once the deanonymization is done, the deanonymizer can disclose the true signer to any other third party, And this is an adaptation of Chom's undeniable signature. It's a very straightforward adaptation of that. And here the verifier chooses some random values, T and U, and computes capital C equals TG plus UQ. And the deanonymizer has to compute the value of D, which is P times C. And this D has to equal T times P plus U times R for the tuple to be linear. Now, the authority shares, but the deanonymizer doesn't directly share D because there is a chance of the verifier being dishonest. So instead, it makes a commitment H, which is the hash of Z, and the authority now has to share T and U to prove to the deanonymizer that T, U are indeed the values that the verifier knows, and that is how C is constructed. The deanonymizer verifies that and shares, once the verification works out, the deanonymizer shares D to the authority, and then the authority can check whether the commitment of D actually works, and then D actually is equal to TP plus UR. If both of the checks succeed, the authority accepts the proof. Now we can continue to our last section, legally binding commitments. So before that, we need to discuss the blockchain model that we assume. We assume a Monero-like ring signature-based system with UTXOs. However, we need an extra functionality on what Monero has got. And it is not difficult to imagine how that can be implemented. We assume that the UTXOs have an internal state, just like Ethereum accounts, and internal state can be manipulated by some scripts that are written on the UTXOs. And we assume that the spend function must return true if it exists for the UTXO spend to work. By which I mean if the UTXO does have a spend function, then whoever wants to spend that UTXO has to pass the parameters to spend in a way that the function returns true for the transaction to be valid. And when the spend function does exist, then the UTXO doesn't need a ring signature. And this is not a problem because normally we would use it in a way so that it has only one output. So it is really an extension of the original transaction that created the UTXO as a payment. Now, the first kind of commitment we construct is a seller-buyer commitment. So here a buyer wants to buy something and a seller wants to sell something. And the seller first goes on and advertises the thing. And the payment the seller expects is in cryptocurrency. And what the contract is that once the buyer pays the seller in cryptocurrency, the buyer gets a commitment from the seller in exchange to deliver the goods. So the goods are not crypto, but the payment is in crypto. So here is the simplified flow where the seller first creates a seller temporary public key S, and buyer also and then publishes the advertisement for the contract, product or service, and then the buyer constructs a similar temporary public key and responds to the advertisement, and this creates a defilement channel where they both share a key, key named K, and then they do some negotiations over this encrypted channel, and at the end of the negotiations, the buyer creates a smart contract reflecting the contracts and deals, and it is constructed in a way so that when the seller spends this UTXO smart contract, she has to sign it in a way so that her identity is disclosed to the buyer using a designated deanonymizer ring signature. So here is how the contract looks. So when the buyer creates the contract, he sets this timestamp, the creator, which is the buyer, the committer, which is the seller, and the content of the contract. These are global variables saved in the UTXO, and when if the seller doesn't sign the contract, then the buyer has the opportunity to claim his money back. And so here this condition is when the spender is the creator, which is the buyer himself, and the timestamp is the creation timestamp plus a delta t, which is the allowed time within which the seller must sign. Then a simple signature verification allows the creator to spend the amount, or that would allow him to reclaim his own payment. Otherwise, if the spender is the committer, which is the seller, then the verification is a signature verification of a snort signature on the temporary key that she created, and then a DDR signature or designated de-anonymized and designated de-anonymizer ring signature, where the de-anonymizer has to be the creator. And if both the signatures verify as true, she gets to spend the amount. So how it works is, if she spends the amount, now the signature is there, the buyer knows her identity, and buyer can prove her identity in case she doesn't fulfill her commitment. The other kind of commitment we work on is a multi-party commitment, where every party takes part as an equal, and the system so there is a problem with that kind of a system where when you sign, your name gets de-anonymized to other parties, but if they have not signed yet, so you don't know their identity. So there is an information mismatch. To handle that, what we do is everyone locks their fund in the contract, except for the first one to sign. And whenever you sign the contract, you disclose your identity to the other parties, and you then also permanently lock the funds of the next one to sign, and you unlock your own. So let's continue and see how that works. So before we continue, since the signing occurs in contract creation occurs in opposite order, we want to make sure what we mean by previous and next party. So let's say we have these parties from 1 to 3 up to n, then the next means the next party of 2 is 3, and the previous party of 3 is 2. Okay, we got that out of the way. Now the contract has 3 internal states, the UTXO. One is pre-locked, when you get the state when the UTXO is created. Then it gets locked when your previous party has signed the contract, and it becomes inactive when you reclaim your money. So how it works is in the beginning everyone does exactly the same thing as the seller buyer contract, where everyone generates a temporary public key, and then that is used to construct a defilement channel pairwise, and they can use these channels to communicate. So once the contract has been finalized, so it also needs to be finalized that who is going to sign first and second, and so on. So the order has to be fixed, and after that has been fixed, you start with the nth party, and the nth party creates a contract that locks his own fund and basically claims that I am open to sign this contract, and this locks his money for some time up to a certain limit. And when he signs, the previous party can initialize his own contract, and he can then create it in a way so that when he can unlock his own contract while locking the funds of the next party. So once these pre-lock steps are done, now the first party can sign, and when she signs, her identity is disclosed to the other parties, and that locks the funds of the second party permanently. So if he doesn't sign the contract now, he would lose the fund. And then when it signs his own, when he also signs the contract, the identity of the second party is also disclosed to everyone else, and that locks the third party, and this continues on until the last one signs the contract. This is the design of the contract. So the init basically is used to construct the contract when the party actually pre-locks his own fund, and when the previous party signs, the lock function is called. So what the lock function does is it verifies the signature with the previous party. So it basically says the previous party has signed with the private key of the temporary public key he was using, and he also must provide a DDS signature where the deanonymizers are the peers that are taking part in the contract. And if both of them are true, then it is locked. So you call the lock function on the contract of the next party, and then you can lock his fund by disclosing your own signature. And when you spend, it is checked that if it is pre-locked, then you can claim your own money after the time limit has spent. And if you are the creator of the account. And in the other case, when you can when the state is locked, then you have to disclose your own signature to spend it. So your identity would be disclosed. And if there is a next party, if you are not the last party, then you would lock that party's transaction. So then the next party also has to disclose their identity, actually give the signature or sign the contract and give up their identity to unlock their fund. Now, in summary, we propose a mechanism to allow people to advertise contracts anonymously, and it's signing the contracts de-anonymize the signers to the other parties while also keeping them anonymous to everyone else. And the party can prove the de-anonymized version of any other signature. So the party can prove the identity of the of any other signer to any judge in the court of law if required. And that's the end of my presentation. Thank you for listening.